Hi, and this is Dr. Habib Ahmed. We are building the foundational concepts towards this course of nano-characterization techniques. In this regard, we will learn about some miscellaneous topics. First, I will discuss the steps involved in the production of silicon from sand. Second, I will explain the Czochralski Crystal Growth method. Third, I will demonstrate the float zone crystal growth technique. Fourth, I will talk about the semiconductor wafer preparation process. Fifth, I will show you how to identify silicon wafers based on their primary and secondary flats. And finally, we will learn how to analyze phase diagrams. Especially, we are going to analyze the silicon germanium phase diagrams. So let's discuss the steps involved in the production of silicon from sand. This image outlines the process of converting raw silicon dioxide into high purity single crystalline silicon wafers used in semiconductors. In the first step, we convert the silicon dioxide into metallic silicon. The silicon dioxide found in sand or quartz is reduced to silicon by reacting silicon dioxide with silicon carbide at high temperatures to form impure metallic silicon, as you can see over here. In the second step, the metallic silicon is converted into trichlorosilane, which is then further purified through distillation process. And I'm going to show you in the next step the process of chlorination and distillation. Then the trichlorosilane in this step is converted to polycrystalline silicon. Trichlorosilane, as shown over here, is decomposed at high temperatures to create ultra pure polycrystalline silicon. You will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 nines over here. And it's called 11 in purity. So whenever you are dealing with material sciences, you buy dopant materials, for example, or you're dealing with crystals, single polycrystalline materials, you say this is 4 in purity, 5 in purity, 7 in purity, 11 in purity. Sometimes it's like 4 in 5 kind of purity, etc. So 11 in purity means 99 point, and then add 9 more nines to it, % pure silicon. But it's still not single crystalline silicon. In order to convert it into single crystalline silicon, we have to process it through either Czochralski's growth method or float zone technique, which are the primary methods for converting the polycrystalline silicon into single crystalline silicon ingots. And then through further processing, dicing and polishing, etc., this single crystalline ingot is then further converted into wafers. So this series of transformations turns raw silicon dioxide into ultra pure silicon wafers essential for electronics. And here is a more detailed representation of the same process. This image illustrates the production of semiconductor grade polysilicon, a critical material for electronics, through several stages. In the first stage, we have sand or quartzite. The process begins with this sand or quartzite, which is actually a silicon carbide, and carbon, we can call it coal as well. These raw materials are heated in an arc furnace at a high temperature of 1800 degrees C. The high temperature causes reduction reaction. You can see silicon dioxide is reacted with either carbon or silicon carbide, reducing oxygen from silicon dioxide, and now we can see we have silicon and carbon dioxide, which are the products. And this process actually produces metallurgical grade silicon, which is 98% pure. Then in the next step, we convert the metallurgical grade silicon into trichlorosilane. So it involves converting the metallurgical grade silicon into a more refined form. Silicon is reacted with hydrogen chloride in a chlorination and distillation unit, forming a mix of trichlorosilane and other components. And these are separated through multiple fractional distillations in order to achieve a purified form of trichlorosilane. This material is called trichlorosilane. The next step is chemical vapor deposition process. In this step, the purified trichlorosilane is then fed into a chemical vapor deposition reactor at a temperature of 1100 degrees C. Inside the reactor, this trichlorosilane reacts with hydrogen, depositing silicon on rods in the form of hyper-pure polysilicon chunks. And this step achieves an extremely high purity level of, you can see over here, if you count the number of 9s, it's 11 in purity silicon, and this silicon is called semiconductor grade polysilicon. So the reactor actually grows polysilicon rods through this deposition process, which are later processed into semiconductor grade silicon. The final product has an incredibly high purity required for advanced semiconductor applications. This multi-step process transforms the quartzite into highly purified polysilicon through reduction, then chlorination, followed by distillation, and finally chemical vapor deposition, making it suitable for manufacturing electronic components. This table outlines the key concepts in obtaining semiconductor grade silicon through a multi-stage chemical process. And here is how we can look at it. So in step 1, the silicon dioxide is heated with the carbon or silicon carbide, typically in the form like over here, to produce metallurgical grade silicon, which we already discussed is 98% pure. And this reaction takes place at a high temperature, as we discussed in the previous slide, 1800 degrees C, reducing silicon dioxide into impure liquid. So as you can see over here, this silicon is in liquid form, while releasing silicon monoxide and carbon monoxide gases. Step 2 is conversion to trichlorosilane. Now, the metallurgical grade silicon, which is 98% pure, is further purified through a chemical reaction with hydrogen chloride, forming trichlorosilane gas, which is a key intermediate in the purification process. And then in the third step, it's also called the Siemens process for semiconductor grade silicon. In this Siemens process, the trichlorosilane gas is reacted with hydrogen gas in a high temperature reactor. We saw it in the previous slide, 1100 degrees C, depositing pure silicon onto rods and releasing hydrogen chloride as a byproduct. This reaction results in semiconductor grade silicon, which has 11 in purity, which is extremely pure and suitable for use in electronic devices. So basically, this process involves first the reduction of silicon dioxide to form metallurgical grade silicon, which is 98% pure. Second, chlorination of the metallurgical grade silicon to form trichlorosilane. And third, deposition of pure silicon through the Siemens process, achieving the high purity silicon required for semiconductor. Each step plays a crucial role in purifying silicon for electronic applications. Now, here are the steps involved in the production of silicon from sand. Now, let us talk about each step individually. Starting with the raw silicon. Silicon is abundant, making up approximately 25.7% of the Earth's crust, mainly as silicon dioxide, a critical resource for semiconductor. The processing of silicon dioxide involves two steps. First, refining to purify the silicon. As we discussed, the reduction process, then the chlorination, distillation, and finally the chemical vapor deposition process. And then crystallization to form usable polycrystalline or monocrystalline silicon. The starting material, as we discussed, is quartzite, a type of quartz sand, silicon dioxide, which undergoes refining and crystallization to produce high purity silicon. So silicon's natural abundance and straightforward refinement makes it essential for semiconductor manufacturing. This slide discusses metallurgical grade silicon, a key intermediate product in silicon production. We discussed the quartzite actually reacts with carbon to produce metallurgical grade silicon and carbon monoxide at a temperature of 1800 degrees C. And this metallurgical grade silicon contains 98% pure silicon with impurities like aluminum or iron. Metallurgical grade silicon is mainly used for industrial purposes such as aluminum silicon alloys and silicones, where silicones are actually a group of synthetic polymers made up of repeating units of silicon, oxygen, carbon, and hydrogen. This slide explains the process of producing electronic grade silicon, which is a highly pure form of silicon used in semiconductor devices. And the chemical reaction involves the reaction of metallurgical grade silicon with hydrogen chloride gas, producing silicon compounds, primarily the trichlorosilane, which is crucial for silicon purification. Then in the purification process, trichlorosilane is distilled to remove impurities, leaving highly pure silicon compounds. Then we have the chemical vapor deposition process, in which the purified silicon trichlorosilane reacts with hydrogen in a chemical vapor deposition process, resulting in polysilicon and hydrogen chloride gas. This produces highly pure silicon for electronics. So the takeaway point here is that electronic grade silicon is made by reacting metallurgical grade silicon with hydrogen chloride, purifying trichlorosilane, and using chemical vapor deposition to deposit pure polysilicon. Now, I'm going to explain the Czochralski's crystal growth method. The Czochralski's crystal growth process is a widely used method for growing single crystals, particularly silicon, which is essential in semiconductor manufacturing. Here is a breakdown of the process. It starts with a small crystal seed, as you can see over here, indicated over here, which initiates the crystal growth. The seed crystal is dipped into a molten material contained in a crucible. Like for example, if we talk about silicon, then the melting point of silicon is approximately 1400 degrees C, slightly above 1400 degrees C. So silicon is melted above that temperature, and this crystal seed is dipped into the molten material, which is contained in a crucible, indicated over here. The material we heat the material, for example, silicon, beyond its melting point using heaters surrounding the crucible. The seed crystal is carefully lowered into the molten silicon over here. Once the seed touches the melt, it begins to cool slightly, initiating the growth of the single crystal silicon. And then the seed is then slowly pulled upwards at a particular rate and rotated simultaneously. This pulling process is done under controlled conditions to ensure that the crystal grows in a uniform manner without any kind of defects. And this process is actually demonstrated over here as well. So the continuous pulling and cooling cause the material to solidify. So we pull it and we rotate it, and then the melt has a particular temperature. So when we start pulling the seed, it starts the material to cool and causes the material to solidify, forming a long cylindrical ingot of single crystal material, which is also seen on the right side. We call it the silicon ingot. This method is ideal because the pulling process ensures that the atoms arrange themselves in a perfect crystalline structure as the material cools. Now here are the key features of the Czochralski's growth method. First, it's a control method. By controlling the temperature, the pulling rate, and rotation speed, the size and quality of the crystal can be managed. And secondly, this Czochralski's process is known for creating single crystal, or we can call it monocrystalline silicon material, with minimal imperfections, which is essential for electronics manufacturing. The process is famously used for growing silicon ingots, which are later sliced into wafers to manufacture semiconductors used in electronics like computers and smartphones. Here is another depiction of the same process. The Czochralski's process is critical for producing large high-purity single crystals, especially for materials like silicon used in the semiconductor industry. The feed material, for example silicon, is placed in a cylindrical crucible. You can see it over here. It's in granular form, so it's placed inside this crucible over here, and then it's heated to above the melting point of silicon using either resistance heaters or radio frequency heaters surrounding the crucible. Once this raw material or the polysilicon is fully molten, a small seed crystal, typically a few millimeters in diameter, is lowered into the surface of the molten silicon. The seed crystal serves as the foundation for the growth of larger single crystal silicon ingot. So the seed crystal is dipped into the melt, and then the seed crystal is gradually pulled upwards while the melt solidifies onto the crystal in a controlled manner. As the silicon continues to grow, its cylindrical shape is maintained by adjusting the pulling speed and the temperature. And the result is a long cylindrical single crystal silicon ingot. As we already discussed, that the rate of pulling and the temperature of the melt are precisely controlled to ensure that the crystal grows in a uniform defect-free manner, and the heaters maintain the material at the right temperature for continuous crystal formation. And here is this a different representation of the same process. We can see it over here as well, starting with the polysilicon chunks, and then here is the silicon single, the crystal seed dipped into the molten state, and then we start pulling it, rotating it. The pulling rate, the rotation rate, and the temperature of the melt defines the diameter of this silicon ingot. Here is another depiction of the same process. So high purity silicon is melted in a crucible made up of silicon dioxide. So as you can see, this is the quartz crucible, silicon dioxide crucible within a furnace, and a small pre-existing single crystal silicon attached to a seed holder is dipped into the molten silicon. The crucible is made up of silicon dioxide. It can hold the molten silicon, and it's heated externally using heaters surrounding the crucible. The entire process is conducted in an inert atmosphere, usually by the introduction of inert gas like argon, to prevent contamination. And silicon monoxide and carbon monoxide byproducts may be generated, and they can be removed as well from the chamber. A thermal shield is actually also applied, which helps maintaining a stable temperature gradient, which is crucial for high quality crystal growth using the Czochralski's growth method. And here is another depiction of the same process. As you can see there, the pull rate, the melt temperature, and the rotation rate are critical over here. This image highlights the key aspects of impurities in Czochralski's silicon crystal growth method. Oxygen is the most prevalent impurity in the Czochralski's growth method, typically with concentrations in the range of 5 to 10 to the power of 17 per centimeter cube. Similarly, carbon concentrations are much lower, in the range of 5 to 10 into 10 to the power of 15 per centimeter cube. The solubility of oxygen in silicon is high, approximately 10 to the power of 18 per centimeter cube at the melting point. As we know that we have to melt the silicon above 1400 degrees C, and the solubility of oxygen is high at that temperature, but it decreases drastically at room temperature, creating a tendency for oxygen precipitation. High oxygen concentration can result in the formation of electrically active defects, which may affect the semiconductor properties. And this diagram shows the temperature gradient in the crystal growth furnace with side and bottom heaters. So you can see the side heaters and the bottom heaters over here. These side and bottom heaters regulate the melt and crystal growth environment. So these factors impact the quality of single crystals used in semiconductor devices. This slide provides insight into the role of oxygen in Czochralski's silicon growth process, and it also shows its benefits. Oxygen in the Czochralski's growth method acts as a gathering agent, trapping trace metal impurities within the crystal, a process which is also known as internal gathering. And this enhances the crystal purity. Also, oxygen helps in pinning dislocations. These are like slightly advanced concepts in material sciences. And these pinning of the dislocations make the crystal structure stronger and more resistant to defects. Oxygen precipitates within the wafer core, reducing stacking faults, making the silicon more robust especially during thermal processing. Also, the presence of oxygen makes the Czochralski grown silicon highly resistant to thermal stress, which is critical in the manufacturing of integrated circuits. So, due to the enhanced mechanical and thermal properties imparted by oxygen, Czochralski's grown silicon is preferred for integrated circuit production, especially in processes involving high temperature steps. Like, for example, if you want to grow MOSFETs, you might like to perform oxidation and then ion implantation steps, and the ion implantation might then require annealing at high temperatures above 1000 degrees C. So if the wafers are mechanically and thermally stable, you can perform these kind of processes. So these points actually highlight the importance of oxygen in improving the mechanical properties and the thermal stability of Czochralski's grown silicon, making it ideal for semiconductor applications. So actually the oxygen impurities in the Czochralski's grown silicon can go both ways. It can be useful and it could be counterproductive as well, depending on the application. Here is an actual picture of the Czochralski equipment to get an idea about the dimensions. The equipment dimensions for industrial silicon productions typically include a chamber height, which could be like 2 to 3 meters, then a chamber diameter, which could be 1 to 1.5 meters, a crucible, which can have a diameter from 18 to 24 inches for 300 millimeter wafers, and a height of like 12 to 20 inches. The crystal length could be 1 to 2 meters, and the crystal diameter sizes are like 100 millimeters, 200 millimeters, 300 millimeters, up to you can say 450 millimeters. And this slide gives you an idea about the height of the silicon ingot. So this person apparently seems like a tall person, and you can see that this silicon ingot has a height which is like, this person might be around 6 feet, so this silicon ingot appears to be taller than that, around 6.5 feet I would say. So the entire system, including heaters, the rotational mechanism and cooling systems for the Czochralski growth equipment might actually occupy several square meters, like an entire lab. This slide discusses how impurities or dopants are added to a molten semiconductor during the fabrication process, such as for doping the material to make it either P-type or N-type. So far we discussed the growth of silicon crystal ingots using the Czochralski's growth method, but also you know that when we buy wafers, it could be intrinsic, it could be P-type, or it could be N-type. So how do you make it P-type or N-type? We add impurities in the semiconductors, and these impurities dope it either N-type or P-type, depending if they are pentavalent or trivalent impurities. So let's start with the basics. What are impurities? Impurities are atoms or elements added to a semiconductor material to change its electrical properties, usually to make it a better conductor, and this process is called doping. Now the question is, how do impurities behave in a melt as compared to when they are solidified? Like, for example, we melt the silicon in a crucible and above like 1400 degrees C, then how are the dopants going to react, or you can say act, in the molten state inside the crucible as compared to when we solidify the molten silicon into single crystalline silicon ingot. So when impurities are added to the molten semiconductor, they don't always want to become part of the solid material. Impurities have a tendency, like mostly, to stay inside the liquid, the liquid or the molten silicon materials. Many impurities prefer to stay in the liquid rather than becoming incorporated into the solid structure of the semiconductor, and this tendency is described by segregation, or you can say segregation coefficient. What is segregation coefficient? Segregation coefficient demonstrates the behavior of impurity, or how much of it gets incorporated into the solid versus how much stays in the liquid. And this measurement is called segregation coefficient, or you can say segregation coefficient is the ratio of impurity in the solid to impurity in the liquid. Like we talked about this process, let's go to some slide, like for example this one. So if we add impurities into this melt, segregation coefficient is the ratio of impurities in this solid, the silicon ingot, to the impurities in this liquid. So a low, and we represent the segregation coefficient with K. So a low value of K, which is close to 0, means that most of the impurity stays in the liquid, and a high value of K close to 1 actually implies that the impurity distributes equally between the solid and the liquid. And some examples of impurities are aluminum, boron, and phosphorus in silicon. For aluminum, the segregation coefficient is 0.002, meaning that it almost always stays in the liquid with very little getting incorporated into the solid. Now, as compared to that, the segregation coefficient of boron is 0.8, meaning that it shows less preference for staying in the liquid, and it's more likely to be found in the solid. So it's comparative. So it means that boron has a better tendency getting into the solid, into the single crystalline silicon ingot, as compared to aluminum. And then the segregation coefficient of phosphorus is 0.35, meaning that it has a moderate tendency to go into the solid. However, there is another problem with phosphorus. Phosphorus also evaporates from the melt at a high rate, which adds complexity to its behavior during the process. So, I mean, the takeaway point is that we know that in order, for example, compare boron versus phosphorus doping of silicon. We know in order to dope silicon p-type, we need to add a trivalent impurities such as boron. And in order to dope silicon n-type, we need to add a pentavalent impurity such as phosphorus. So looking at the segregation coefficients, it means that it's going to be easier to dope silicon p-type with boron as compared to dope it n-type with phosphorus. So in other words, you can say that the takeaway point of this slide is that impurities have different preferences for being in the solid semiconductor versus the liquid melt. And this behavior is characterized by the segregation coefficient. It's crucial in controlling how much of the impurity ends up in the final solid material. Some impurities like aluminum prefer to stay in the liquid, while other impurities like boron have a higher chance of being incorporated into the solid. Here I'm going to demonstrate the how to define the dopant concentration nomenclature. So like how to classify materials into lightly doped, and heavily doped materials. We know that for n-type doping, we use a pentavalent impurity like phosphorus, and similarly for p-type doping, we use a trivalent impurity like boron. If the doping concentration is less than 10 to the power of 14 per centimeter cube, we classify it as very lightly doped materials, and we represent it with n minus minus, where minus minus is used as the superscript. Similarly, we can have like very lightly doped p-type material represented with p minus minus. Similarly, doping concentrations in the range of 10 to the power of 14 to 10 to the power of 16 can be classified as lightly doped material, and we represent it with n minus or p minus. Doping concentrations in the range of 10 to the power of 16 to 10 to the power of 19 is classified as doped, and we represent it with n or p. Similarly, doping concentrations with greater than 10 to the power of 19 per centimeter cube are classified as heavily doped, and we represent it with n plus or p plus. Here I demonstrate the float zone crystal growth technique. Float zone growth is a widely used method for producing high purity defect-free silicon crystals, particularly for semiconductor applications. And the concentrations of impurities like carbon and oxygen are extremely low in float zone technique as compared to its contemporary Czochralski's growth method. In Czochralski's growth method, we know that oxygen actually improves the thermal stability and the mechanical properties. You can say the mechanical strength of the silicon wafers. Similarly, in float zone technique, another light impurity, nitrogen, helps to control micro defects, and it also brings about an improvement in the mechanical strength of the wafers, and it is intentionally added during the growth stages. Here is a representation of the float zone technique. In fact, I've added different figures so that you can have a better intuition about the process. In the float zone technique, we actually have a radio frequency field. In another picture, you can see here is the radio frequency field represented over here as well, and you can see here the RF radio frequency coil can be seen over here as well. The core principle of the float zone growth involves traveling of this radio frequency coil, which generates a magnetic field, and this heats a specific zone of the polycrystalline silicon rod, creating a molten zone. So in float zone, we actually start with the rod, and this rod is polycrystalline, it's not monocrystalline. And this radio frequency coil actually helps melt this zone of the polycrystalline rod. This process does not require a crucible, and due to this property of not requiring the crucible, it has reduced risk of contamination as compared to the Czochralski's growth method. The entire process occurs in an inert environment, usually argon. You can see here the gas inlet can be introduced. Gas can be introduced from here. Inert gas could be argon. To prevent oxidation and contamination during the crystal growth process. So how does it work? So the way it works is, initially a seed crystal So here is the polysilicon rod. Let's start with this image. Here is the polysilicon rod. Here is the radio frequency coil represented with this small ring, and here is the single crystalline seed crystal. The seed crystal is introduced from below the polycrystalline silicon rod, and the radio frequency field actually partially melts the tip of the silicon rod, forming a molten zone. The single crystal silicon is then brought into contact with this molten zone. The seed acts as a template for the subsequent growth of the single crystalline silicon, ensuring that the newly grown silicon maintains the correct crystal orientation. There is a necking kind of process in the float zone technique. Once this seed touches the molten zone, the necking process begins. As you can see over here, the neck is formed by slowly reducing the diameter of the molten zone. Now, what is the purpose of necking? This is a crucial step in eliminating the dislocations within the crystal. By controlling the diameter, the growth of the dislocation-free material is ensured, setting up a perfect crystalline structure. So here you see a taper formation. After the necking process, the molten zone is gradually widened, as you can see, this tapered region, to increase the diameter, and this forms a taper. This taper allows the crystal to smoothly reach the desired diameter for the steady state growth, and the control taper ensures that the crystal growth transitions smoothly from the narrow neck to the desired diameter. And once the desired diameter is achieved, the radio frequency coil continues to move along the rod, maintaining the molten zone and allowing the crystal to grow steadily. The single crystal grows from the seed and follows the orientation of the seed crystal, ensuring the resulting silicon ingot has a uniform crystalline structure. And then here are a couple of terminologies that I want you to know. This polysilicon rod is called the solid rod, and this single crystalline grown rod is called the solidified rod. Let's talk about the key benefits of the float zone technique before we discuss the concentrations of impurities in the solid to the impurities in the liquid and segregation coefficient. So here are the key benefits of the float zone technique. First, it's a high purity method. Since no crucible is used, the process eliminates the risk of contamination from the container materials, resulting in ultra pure single crystal silicon material. Secondly, it's a defect-free growth. The necking process and careful control of the crystal growth helps produce dislocation-free crystals, essential for high-performance electronic devices. Third, it has low oxygen content. Float zone technique growth typically results in lower oxygen contamination compared to the Czochralski's growth method, which makes the float zone growth technique silicon ideal for high power and radiation sensitive applications. So the float zone growth method is vital for producing high quality silicon with minimal defects and impurities. It is especially useful in industries requiring ultra pure materials such as power electronics, solar cells, and semiconductor devices. By carefully controlling the radio frequency heating and the movement of the molten zone, we can produce large single crystal silicon ingots with precise structural characteristics. In float zone crystal growth, the impurities and dopants have different behaviors due to their tendency to remain in the liquid phase rather than the solid phase. And once again, this is due to impurity segregation. So here is the molten zone. As the molten zone moves along the silicon rod, the solidifying crystal behind the molten zone tends to reject impurities. And this is due to the fact that most impurities prefer to stay in the molten silicon rather than being incorporated into the solidified crystal. And this tendency is quantified using the segregation coefficient, which is the ratio of impurity concentration in the solid to the impurity concentration in the liquid. For many impurities, as we already saw, that the value of K, which is the segregation coefficient, is less than 1, meaning that most impurities concentrate in the liquid and effectively they are pushed along the molten zone. So with the passage of time, more and more concentrated impurities stay in the molten zone. Now let's talk about this diagram. In this diagram, Cs of x actually refers to the concentration of impurity in the solid rod at a given position x. So as we already discussed, that polysilicon, we are referring to the polycrystalline silicon as the solid rod and the single crystalline silicon as the solidified rod. C naught is the initial concentration of impurities in the solidified rod. So as the molten zone moves, impurities accumulate at the interface between the solid and the liquid, and they are not evenly distributed. The further you move along towards this polycrystalline silicon rod, the concentration Cx changes, showing how impurities are effectively segregated or more and more accumulated during the process. So, which also means that if you want to purify the crystal, you can pass it through multiple phases. Like you can pass it through one run of the float zone process, and then through the second one, and through a third one. So multiple passes can be done of the float zone process. Each pass reduces the concentration of impurities by moving them to the end of the rod, to the solid end of the rod, and the contaminated end can later be removed, leaving behind high purity silicon. So over several passes, the impurity concentration is progressively reduced, refining the silicon to very high levels of purity suitable for semiconductor applications. So this is the key advantage of the float zone technique, its ability to reduce impurity levels without the need for a crucible, which minimizes contamination. And as a result, the silicon grown through the float zone method has much lower concentration of metallic and oxygen impurities compared to the Czochralski growth method, which makes it ideal for high power and high performance devices. So the float zone technique is actually a highly effective method for growing pure defect-free silicon crystals by the segregation of impurities during the solidification, and this process ensures that the resulting silicon is of extremely high quality, essential for high performance electronic devices. Let's talk a little bit about the segregation coefficient once again, which is the ratio of impurity concentration in the solid phase to that in the liquid phase during the crystal growth process. As we can see over here, boron has a segregation coefficient of 0.8. So it has kind of even distribution between the solid and the liquid, making p-type float zone growth more homogeneous for doping. Then we see that the segregation coefficient for phosphorus is 0.35, which means that silicon concentrates in the liquid, and N-type doping is less homogeneous in the float zone growth process. And also it's because phosphorus also evaporates from the melt. So the takeaway point is that a high value of K close to 1 results in more uniform doping, and a lower value of K actually makes it harder to achieve uniform doping, especially in N-type doping of silicon. This graph illustrates the segregation fraction during the float zone refining process for different impurities, for boron, phosphorus, arsenic, and antimony. It shows how the concentration of impurities in the solid rod, denoted as CS, changes relative to the initial concentration of impurities in the melted material, represented with CO. So, or you can say the solidified rod. CO is the concentration of impurities in the solidified rod. The graph actually demonstrates how different impurities behave during the crystal growth and helps predict the distribution of these impurities in the final solidified material based on their segregation characteristics. So the y-axis, or the vertical axis, actually is CS divided by C naught, the ratio of impurity concentration in the solid to the concentration of impurities in the solidified rod. And the horizontal axis is actually the fraction of the melt solidified. So, so it means that 0 means that we are starting with the polysilicon rod and then moving towards 1. 1 actually means that all the solid rod, the polysilicon rod, has been converted to the single crystalline solidified rod. Then let's talk about the impurity behaviors, starting with boron. Boron has nearly constant concentration, indicating uniform distribution throughout the solidification. Talking about phosphorus and arsenic, they gradually increase as the solidification process continues, and it's less uniform as compared to boron. And then talking about antimony, antimony has a sharp increase in the concentration near the end of the solidification, indicating a strong segregation towards the end. So then the takeaway points are that boron actually provides more uniform doping throughout the solid rod, making it easier to produce p-type silicon wafers. On the other hand, phosphorus, arsenic, and especially antimony concentrate heavily towards the end of the solidification process, making it harder to achieve uniform doping in N-type materials or when the impurities are present. Here is a comparison between the Czochralski's growth method and the float zone technique in terms of key factors like the growth rates, the oxygen and carbon content, and the production characteristics like the production diameter. In terms of the growth rates, I've copied this table from somewhere, I forgot, but actually here it's shown that float zone is faster, but in reality, because the Czochralski's growth method involves growing silicon ingot from the melt, it's actually faster. It's like the growth rate is like 1 to 3, in the range of 1 to 3 millimeters per minute. On the other hand, the float zone is slower, like in the range of 0.5 to 1 millimeters per minute. So you got to make the corrections over here. Talking about oxygen and carbon content, we have high oxygen and carbon content in the Czochralski's growth method due to the crucible contact, while we have low oxygen and carbon content in the float zone technique because we don't have any contact with the crucible in the float zone growth technique. Talking about the production diameters, this is a relatively older reference, but using the Czochralski growth method, we can grow larger diameters up to 300 millimeters, and using the float zone technique, we can have smaller diameters up to like in the range of 100 to 200 millimeters. The Czochralski growth method introduces more impurities like oxygen and carbon and higher dislocations. The float zone technique has higher purity and lower dislocation density. If you compare them in terms of cost and scale, the silicon wafers produced using the Czochralski growth method are cheaper and are also used for mass production. The silicon ingots produced using the float zone technique are more expensive and used for specialized ultra pure material based devices. So to summarize this table, the Czochralski growth method is faster, cost effective, results in larger diameters, but it has higher impurity content of oxygen and carbon. On the other hand, the float zone growth technique is slower, more expensive, results in smaller diameters, but has extremely high purity and lower impurity content. Now we talk about the semiconductor wafer preparation process. Here is an elaboration on each step shown in the wafer preparation process. We start with the crystal growth, and this step begins with the growth of single crystal ingot using Czochralski's method or float zone technique from polycrystalline silicon. Then we have the single crystal ingot. After the single crystal growth, we have a long cylindrical ingot. This ingot must have a uniform diameter and it should have a crystalline orientation throughout. The ingot will be further processed to create thin flat wafers that will serve as the substrates for microchips and integrated circuits and other kind of devices. So then we proceed with the crystal trimming and diameter grind. This process involves in mechanical grinding of the ingot to achieve a precise uniform diameter, and for this purpose we remove any surface irregularities or defects from the ingot. So like the ends of the ingots are tapered, and we actually take away these tapered parts in order to have a uniform diameter of the wafers. And then the next step is flat grinding, as you can see over here. The surface of the ingot is ground flat to ensure smoothness and consistency across the ingot surface. And this provides a reference flat for orientation as well during the wafer processing, and it prepares the ingot for slicing into wafers. And then we proceed with the wafer slicing process. The trimmed ingot is sliced into thin circular wafers using a precision wire saw or diamond saw. Each slice is just a few hundred micrometers thick. Like generally, silicon wafers are like around 300 micrometers to 500 micrometers thick. And this step actually creates individual wafers that will later serve as the substrate for semiconductor devices. Then we proceed with the edge rounding. The edges of the sliced wafers are rounded using a grinding process. This helps to prevent edge chipping and reduce the risk of wafer breakage during handling. The next step is lapping. After edge rounding, the wafer undergoes lapping, a mechanical process where both surfaces are polished. In some cases, just one surface is polished. In other cases, both surfaces are polished to reduce surface irregularities and thickness variations. The next step is wafer etching. The wafers are chemically etched to remove any remaining surface damage from slicing and lapping processes. And this step involves the use of acid or base solutions. And the purpose of this step is to smoothen the surface and remove any contaminants or imperfections that could actually interfere with the later stages of semiconductor fabrication. Then the next step is polishing, which involves polishing to a mirror-like finish using chemical mechanical polishing. We use slurry over here, seen over here, which is a mixture of chemicals and abrasives used in combination with a polishing pad to achieve the desired surface quality. And finally, the wafers are inspected for surface defects, thickness uniformity, and overall quality. And for this purpose, techniques such as laser scanning or microscopic inspection are used to ensure that the wafers meet really strict, we call it stringent industry standards. So this step-by-step process transforms raw silicon into high quality wafers, the foundation for semiconductor manufacturing. Each step plays a crucial role in ensuring the mechanical strength, the surface quality, and purity necessary for reliable performance of devices. Here is the wafer preparation cycle. We start with the crystal growth, in which silicon ingots are grown using the Czochralski's or float zone technique. Then the ingot is trimmed and ground to ensure uniform diameter and remove any surface irregularities. The ingot is sliced into thin wafers using precision saws for a particular wafer thickness. The surfaces are smoothed using lapping, and the edges are rounded to reduce breakage risk or something. We know that silicon is brittle, so if the edges are rounded, this reduces the chance of breakage of the wafers. Chemical etching removes surface damage from slicing and lapping, and it results in creating of smooth surfaces. The wafers are polished, and it gives a mirror-like look, a defect-free surface which is needed for semiconductor manufacturing. The wafers are thoroughly cleaned to remove contaminants. The wafers are inspected for defects, flatness, and thickness uniformity. And the defect-free wafers are securely packaged for transport and use in fabrication. So now I'm going to slightly elaborate each and every step, starting with the ingot diameter grind. The cylindrical surface of the ingot is ground to ensure a uniform diameter, so we actually remove the tapered edges, and then a flat is actually ground along the side for orientation during later processing. And these steps are essential for preparing the ingot for semiconductor wafer production. This image shows an internal diameter saw used in semiconductor manufacturing to slice thin wafers from the cylindrical silicon ingot. The saw actually cuts with an inner edge, reducing material waste and ensuring precision as well, and also uniformity. So these wafers are critical for producing integrated circuits and electronic components. This image shows a magnified view of a polished wafer edge. The wafer shown is a thin, flat disc typically made of silicon which has been polished to achieve a smooth and defect-free surface. The wafers are used in the fabrication of electronic circuits. And then the focus on the wafer edge highlights the importance of edge treatment. After slicing the wafer from the silicon ingot, the edges are rounded and polished. And this reduces the risk of edge chipping, cracking, or breaking during further processing, ensuring durability of the wafers. So the purpose of polishing, edge polishing, actually is to improve mechanical integrity of the wafer. This image illustrates the chemical etching process used to remove surface damage caused by wafer sawing. When the wafers are cut from silicon ingot using a saw, the process can leave behind surface imperfections, micro cracks, roughness, which can really affect the wafer's quality. So after sawing, wafers are actually submerged into a chemical bath, typically containing acidic or alkaline solutions. This process removes a very thin layer of material from the wafer surface. It smoothens it and it eliminates any residual damage from the sawing process. So the chemical etching actually ensures a clean, uniform surface, crucial for subsequent manufacturing steps such as doping, photolithography, thin film deposition, in order to prevent defects in the final semiconductor devices. This process refines the wafer surface to enhance its performance for semiconductor manufacturing and fabrication. This image illustrates a wafer polishing process. Wafer polishing, specifically chemical mechanical polishing. It's a technique used to achieve smooth and flat surfaces on semiconductor wafers, and it has different components like the polishing head. The polishing head holds the wafer securely in place during the polishing process. It applies pressure onto the wafer as it moves over the polishing plate. Then we have the polishing plate. This actually is a flat surface on which the abrasive cloth over here is placed. The plate rotates, allowing the abrasive action to polish the wafer as it moves beneath the polishing head. Now, what is the abrasive cloth? The cloth which is placed on the polishing plate contains abrasive materials like diamond particles or other fine particles that helps smooth the wafer surface, and the combination of abrasive particles and mechanical force actually removes imperfections from the wafers. And then we have the wafers over here. You can also see the wafers in the actual process over here. Typically silicon wafers, they are being polished in this setup. The wafers are mounted on the polishing head, and during the process they come into contact with the abrasive cloth. So the primary goal of wafer polishing is to achieve a smooth, flat, and defect-free surface. It is essential for high-quality semiconductor devices and manufacturing. And the polished wafers will have a uniform thickness and minimal surface defects and irregularities, damages, and this is vital for processes like photolithography and fabrication. Sometimes we might have single-side polishing. At other times we might also have double-sided polished wafers. And you can see if you see mirror-like look on just one face, it is single-side polished. But if you see mirror-like look on both sides, then this is double-sided polished. And double-sided polished are used for manufacturing vertical devices, and they are going to be more expensive. This slide demonstrates the process of backside gathering to purify silicon, which is a method used in semiconductor manufacturing to improve the quality of silicon wafers by removing impurities, particularly the metallic contaminants. So let's talk about gathering. What is gathering? Gathering is a process used to attract and trap impurities, especially metal contaminants, in certain regions of a silicon wafers. And this ensures the front, which is this side over here, the top side remains pure, which is critical for the performance of semiconductor devices, because we mostly grow devices on the top side. So if this side is more pure, then we can have high quality devices as well. And this is how the process works. So we know that this top side of the wafer is the polished surface where we want to grow the semiconductor devices. On the back side, we introduce argon ions, which are implanted into the wafer at an energy of 50 kiloelectron volts and at a dose of 10 to the power 15 per centimeter square. The argon actually amorphizes the backside silicon. We know that ion implantation introduces damage into it by dislodging atoms from their lattice sides. So then the wafer is then heated up to at 500 degrees C, causing recrystallization, and it's kept at 500 degrees C for several hours. So the argon actually forms microbubbles, preventing damage during annealing. And then there is a gathering process. So the wafer is held at 550 degrees C for several hours, and then the metal contaminants are drawn to this damaged region or the initially amorphized region, and they get trapped by the argon stabilized damage. Once these contaminants are trapped, the contaminants actually stay in the backside region and do not affect the top side, which is the active side for fabrication of devices. The importance of this process is that it significantly improves wafer purity, enhancing the performance and reliability of semiconductor devices by keeping the active side clean. So in conclusion, the backside gathering actually ensures high quality wafers, protecting the front side from impurities and thereby improving the device functionality and longevity and performance. Here I'm going to demonstrate how to identify silicon wafers based on their primary and secondary flats. This image explains the identification of silicon wafers, specifically distinguishing different types of wafers based on their crystallographic orientation. We can call them planes, and doping type. So basically from the primary and secondary flats, we can determine the planes, the growth planes, and the doping type. For wafers having diameters less than 150 millimeter, or you can say 6 inches, flats on the edge of the wafers are used to indicate both the crystal orientation and the doping type. And we can categorize the flats into primary flats as indicated over here. Similarly, in this image, they are indicated on the right side. These are the primary flats. And the secondary flats, like these ones over here, similarly you can see it over here. The primary flats are bigger, the secondary flats are smaller. The primary flat is the largest flat on the wafer and helps indicate the wafer's crystal orientation. Similarly, the secondary flat is smaller and it helps identify the doping type, N-type or P-type. Then we can have different flat configurations. For example, a silicon 100 N-type wafer has a primary flat and a secondary flat located at 180 degrees opposite to the primary flat. Similarly, silicon 111 P-type wafer. So this we are talking about 100. Let's talk about 100 P-type first as well. Similarly, silicon 100 P-type wafer has a primary flat and a secondary flat which is located at 90 degrees relative to the primary flat. Then we have silicon 111 N-type. By the way, this is a typo. It's not A-type, it's N-type. So make a correction over here, please. So silicon 111 N-type has a secondary flat which is located at 45 degrees relative to the primary flat. Then silicon 111 P-type wafer only has the primary flat. It does not have the secondary flat. And only the primary flat is used to identify the wafer with no secondary flat, simplifying the identification. So in conclusion, the primary and secondary flats on the silicon wafers are critical for identifying their crystal orientation and doping type. And this mechanism is important for manufacturers during semiconductor device fabrication, as different orientation and doping types affect the electrical properties and behavior of the wafers. Let's talk about phase diagrams, especially how to analyze the silicon germanium phase diagrams. A phase diagram is like a map that shows how a substance like water or any other semiconductor material changes between solid, liquid, and gas phases depending on the temperature and pressure. So from the phase diagram, we can determine whether a material is in solid phase or liquid phase or gas form, or it can be in mixed form as well, depending on the temperature and pressure conditions. If you heat something, it might go from solid to liquid to gas. Like for example, if we heat ice, it's gonna turn into liquid, which is water. And if we further heat water, it might turn to gas, which is steam. And actually a phase diagram actually helps you see when and how these changes happen. And we can see that for semiconductor materials as well. The lines on the phase diagram actually show the points where the substances change its state, like for example ice melting into water, etc. Here I demonstrate a phase diagram of silicon germanium, an alloy used in high-speed transistors with applications in integrating analog, RF, and digital circuits onto a single chip using existing CMOS technology. So first let's talk about what is silicon germanium. Silicon germanium is an alloy formed by the combination of silicon and germanium. And the key benefit of silicon germanium is its ability to achieve higher switching speeds as compared to the traditional silicon-based semiconductors, making it ideal for high-speed electronics. Now let's have an overview of the phase diagram. This phase diagram plots the relationship between temperature on the vertical axis and silicon composition on the horizontal axis in the silicon germanium material. So as we can see over here, the composition is running from on the x-axis, the composition is running from 0 to 100, where 0 represents 0% germanium, which means that we are actually talking about pure germanium at this point. The 40% point actually means that we have 40% silicon and 60% germanium. Similarly, the 90% point means that we have 90% silicon and 10% germanium. Similarly, the 100% point means that we have 100% silicon and 0% germanium. And the y-axis actually shows temperature in degree Celsius. Also on the phase diagram, we also see the melting points like on the right side we have pure silicon, and the melting point of silicon is 1414 degrees C. Similarly, on the left end we have germanium, and the melting point of germanium is 938.2 degree Celsius. Then we have the solid region, the liquid region, and the mixed region. Where in the mixed region we have liquid plus solid state. In the solid region, the silicon germanium is fully solid. The composition is fixed as a solid phase with varying proportions of silicon and germanium. Then we have the liquid plus solid region, the middle region. And actually, so in this region we have a mixture of liquid and solid silicon germanium. As the temperature drops below this region, we are actually going into the solid region, and as we go higher above this region, the entire material converts into liquid form. Also, if you notice, we have the boundary lines between the solid region and this mixed region, and then there's a boundary line between this mixed region and the liquid region. This line over here is called the solidus line, and this line over here at the top is called the liquidus line. The liquid line is the liquid section is the upper section in which the silicon germanium is fully in the liquid phase. So the solidus line, this line over here, actually indicates that the temperature below which the alloy is going to be completely solid. Similarly, the liquidus line over here indicates the temperature above which the alloy is going to be fully liquid. Then the point is, how do we, if a particular temperature and atomic percent is given, how do we determine what percent of the material is solid and what percent is liquid? And secondly, what percent is silicon and what percent is germanium? So we actually use a line method for this purpose. Like for example, in the next slide, we are assuming that we are heating a material which initially has 40% silicon, atomic silicon. So talking about this point over here, x0, which is the initial point, we start heating the material. So this point actually means that the silicon germanium has 40% silicon and 60% germanium, and then we start heating the silicon. So as the temperature is elevated, the materials begins melting at 1070 degree C. So initially the silicon germanium at 40% content is in solid form, but at this temperature over here, corresponding to a temperature of 1070 degrees C, it enters into the mixed phase. Above 1070 degrees C and below this temperature is exactly 1230 degrees C. So in the range of 1070 to 1230 degrees C, the silicon germanium is going to be in mixed phase. Part of the material is going to be solid and part of the material is going to be liquid. So then there are two questions: how much of the material is solid and how much is liquid? And secondly, in the solid part, what percent is silicon and what percent is germanium? Similarly, in the liquid part, what percent is silicon and what percent is germanium? So we got to determine that. So as an example, we assume a temperature of 1200 degrees C. So now we have to answer these two questions. So assume a temperature of 1200 degrees C, which is exactly this point corresponding to a temperature of 1200 degrees C. And as we move along the 1200 degrees C point, we know for 40% composition, we know that we are in the mixed phase. Part of the silicon germanium material is going to be solid and part of the silicon germanium material is going to be liquid. So now we have to address two questions. One, how much is solid and how much is liquid? And secondly, in the solid part, what percent is silicon and what percent is germanium? Similarly, in the liquid form, what percent of the silicon germanium alloys is silicon and what percent of the silicon germanium material is in solid form? So in order to solve this, we actually use a tie line method. Now what is a tie line method? We draw a horizontal tie line at a specific temperature. The temperature is 1200 degrees C. So we draw this tie line which shows the coexistence of the liquid and solid phases. So we draw this tie line to the solidus line and to the liquidus line. The tie line, the purple line shows its extension to the solidus line, and similarly the green line shows its extension to the liquidus line. And then this purple line intersects the solidus line at this composition, which is approximately 67%. Yeah, 67%. Similarly, this green line intersects the liquidus line at this composition, which is how much? I would say 33%. I would say. So this is 30, you can say this is 33%, and this is 67%. So it means that part of the material which is solid has 67%. In the mixed phase, we have 67% silicon and 33% germanium. So let's move on to the next slides. Like as we saw over here, read off the compositions of the liquid, which means that this is 34% silicon, and in the solid we have 67% silicon. So we can actually note down these compositions. So we look over here, 67% silicon in the solid, and then if we look at the liquid part, we have 34% silicon in the liquid part. In order to address the next question, how much is solid and how much is liquid, we are going to use some formulas. So this blue line actually shows the extension of the blue line to the atomic percent to the horizontal axis shows the initial concentration of silicon, percent of silicon, which is 40%. The extension of the purple line to the horizontal axis shows the percentage of silicon in the solid phase, represented with excess, and the extension of the green line to the horizontal axis actually determines the percentage of silicon in the liquid phase. So we know that x naught is equal to 40, xs is equal to 67%, and xl is equal to 34%. Now, once again, how much of the material is solid and how much is liquid? In order to address that question, we are going to use formulas. Percent solid is equal to x naught minus xl divided by xx minus xl. The values are also given into 100. So 18.2% of the material is solid. Similarly, for the liquid, we can use these formulas, resulting in 81.8%, or simply subtract 18.2 from 100. It means that 81.8% of the material is liquid. So once again, to summarize, we are actually in the mixed phase, and we know that part of the alloy is going to be solid, part of the alloy is going to be liquid. So 18.2% of the alloy is solid, and out of that solid material 67% is silicon. Similarly, 81.8% of the material is liquid, and out of that 81.8%, 34% of the material is silicon. So this is how you approach this problem. You can also assume other temperature. In exam, I might give you determine how much of the material is solid and how much is liquid at 1100 degrees C at a composition of 45% initially, right? So you draw a horizontal line over here. So we come to like this point over here, right where my mouse cursor is. So I may ask you, okay, how much of the material is solid, how much is liquid? And secondly, in the solid part, what percent is silicon? And also in the liquid part, what percent is silicon? So this is how you approach this problem. Silicon germanium has various applications. We can use it in high-speed transistors because silicon germanium transistors offer faster switching speeds as compared to the traditional silicon-based transistors, making them ideal for like analog, radio frequency, and digital applications. And secondly, integration in CMOS technology. Silicon germanium can be integrated into standard CMOS processes. CMOS stands for complementary metal oxide semiconductors. And integration in CMOS technology is more challenging for other materials like gallium arsenide. So, but it can be done for silicon germanium. So this makes silicon germanium ideal for modern chip design without the need for specialized equipments. This phase diagram and silicon germanium's properties make it crucial in semiconductor technology, where the alloy's integration into CMOS processes offers substantial benefits over other semiconductors. This concludes the lecture for today, and I will talk to you next time. Take care. Adios.